Okay, so let's talk about the very general case. So starting with our Reynolds transport theorem, and you probably want to cross this V here, because this is supposed to be d volume. Reynolds transport theorem and our system law for conservation of linear momentum, which this dmv dt is really mass times acceleration, right? So we'll see that our b is f and our beta is v, and let's plug our beta all in, and what we get for our general case is d dt, triple integral over our control volume of v times rho dv plus the integral over control surface v times rho times v dot n dA. Control surface being the edges of our control volume. The control volume itself is the whole middle. That's why we have a dV here and we have a dA for the control surface. And all that equal to the sum of the forces. Okay, so x, this term, is x. That's the net rate of change of momentum inside. So that's our unsteady term. So just like we could have mass building up inside or getting smaller inside, we can also have momentum doing the same thing. And this is the momentum crossing the boundaries. And this is the forces required to keep that control volume in one place or to keep it from accelerating. So let's simplify that a bit. Usually we don't have that totally general case. So starting with the fixed inlets and exits, normally you don't have flow coming in and out all over the place. You have certain regions where it is, so we want to break that down. Makes our lives a little bit better. So we still have this unsteady term, ddt over the control volume, rho v d volume, plus, and what we're going to do here is call this the sum over the outlets of our momentum flux term here. At big M dot vector minus over the inlet, same thing. This is a momentum flux term, not mass flow rate. And I'm going to define that right here. And that's going to equal your sum of your forces. So where big M dot vector is just what we had in that integral, or it is that integral. This time it's over an inlet or exit instead of the whole control surface. And that's going to be your rho times v dot n dA. Okay. So be careful. Don't think that that's mass flow rate. That's momentum flow rate. And you can tell because, first of all, it's a big M, and second of all, because it has the arrow above it, meaning it's a vector. Okay. So that's what we're going to do. Usually use the summations over our inlets and exits. Also, next simplification is steady flow. And for steady flow, basically, we're not going to have a time derivative. If it's steady, that means nothing's changing in time, so we can cross that whole term out. So we can drop the ddt term. And that's all we have to do for steady flow. Most of the time we are going to be talking about steady flow. It gets way complicated if it's not steady flow, at least for conservation of momentum. Conservation of mass we might have unsteady, but not so much conservation of momentum. Okay, so next, let's say we're going to use average velocity, and that's an approximation that we use a lot, just to try to get a good feel for what's going on, but without being totally accurate, but it simplifies our lives a lot because we won't have to integrate then. Another thing that is usually true is we have incompressible fluids, and if it's incompressible, that means rho is constant, and that means it pops out of the integrals, and the derivative, so that helps a lot. So what I mean by average velocity here, lost my pipe for some reason. In reality, if this is a pipe, so we have a z direction and an r direction, say like that, we have a no slip condition. So at this exit, our velocity profile would actually look something like that. probably parabolic. So v here is a function of r in reality. This is actual. But what we can do to make our lives a little simpler, but just remembering this is always an estimation, is use the average velocity. Average velocity, much easier to get. If you, for instance, have a flow rate, you can just divide by area and get an average velocity. So that makes our lives a lot easier in many ways. So average velocity. Still a vector. Okay, we don't want to use peak velocity or some other velocity when we're using these equations. It needs to be average velocity if we're going to make this approximation. Okay, so let's see what happens when we do that to our momentum flux. So we had our momentum flux, m dot vector, was the integral over that inlet or exit of rho times v dot n dA. Okay, so first of all, over that area that we're talking about, over that inlet or exit, to say we were talking about that exit at that pipe, if velocity is not changing with area as you go around in that area, then all these can be treated as a constant, right? So they all come out. So that's going to be rho comes out because it's incompressible, v dot n, the integral over the area of dA. Well, the integral over that area of dA is just a. So our m dot equals rho v dot n a. All right. The other thing we can do then is look at that v dot n. So remember to take a dot product. This should also be a vector. A dot product, you multiply the I terms and then add them to multiplying by the j terms, and then you multiply the k terms and add those up too. When you do all that and you add, you end up with a scalar, not a vector. And that scalar in this case, v dot n, so n would be coming out here. It's a unit vector. V dot n is going to end up just being v. Since if you're using v average, it has to be in the n direction. So what you're going to end up with is v here. V being the magnitude of v average. Okay, so rearranging this a little, let's do rho v, where v is our v average, times area, and then times our v vector, which is still a vector and still left in there. What you see here is rho VA. Hopefully you recognize that. That's our little m dot. That's our mass flow rate. So what happens in this simplified case where we're doing this approximation of V average, our momentum flux just becomes m dot V. All right. And if we also have steady flow, we can simplify the whole conservation of linear momentum down to what we had in that first video. Sum of the forces equals the sum over the outlets of m dot v minus the sum over the inlets of m dot v. Where v is still vector, these are still vectors, so you have to do the separate components, x, y, and z components, or r, z, theta components, but that's the simplest equation. That's what we're going to end up with most of the time.